Quantum Laser Pointers brings you the infamous double-slit experiment right in the palm of your hand. In 1801, English physicist Thomas Young performed this experiment to determine if light was a particle or a wave. A laser shines a coherent beam of light through a film disc containing two parallel slits. Light striking the wall behind the slits produces a classic interference pattern. This surprising result means light passes through the parallel slits not as particles, but as waves.
Visit our website or subscribe to our YouTube channel now. Be among the first to see our new line of double-slit lasers, quantumlaserpointers.com.
In our search to find out what is actually happening at that point in empty space outside the magnet, we have learned a lot. We have discovered that empty space is a complex entity. It can be stretched, as seen in the expanding universe. It can be bent, as understood by general relativity. It's filled with various types of matter fields, force fields, and the Higgs field, according to the Standard Model. The elements of these fields are quantized, massless, and almost energyless. And we know that empty space offers resistance to change in these fields, for example, permittivity and permeability. We know that with enough energy, the elements of a field can bunch up into localized particles with properties like mass, spin, and various types of charges that spew out their own field elements into the empty space around them. But as much as we've discovered, it feels like we're still just scratching the surface. The order in the Standard Model, like the order in the periodic table of the elements, lends itself to the theory that there is an underlying structure yet to be discovered. This, along with the mysteries of dark matter and dark energy, plus the fundamental incompatibilities with general relativity, also speak to a deeper reality. String theory, supersymmetry, and loop quantum gravity are just a few of the candidate theories currently being explored. In that vein, as we approach the end of our How Small Is It video book, we'll take a look at the smallest that small can get. In quantum mechanics, there is a minimum length called the Planck length. It is over 62 trillion times smaller than a neutrino, our smallest elementary particle. This Planck length is as many times smaller than this dot, as this dot is smaller than the visible universe. Theoretically, it is impossible to determine the difference between two locations less than one Planck length apart. This idea takes us back to our first segment on the microscopic, where we saw how light diffraction created the same problem for optical microscopes. As we pointed out at the start of our story, you can't probe a grain of sand with your finger. How are we going to find out what's happening at this Planck level, the level where the quantized field elements operate? This is just one of the many challenges for physicists of tomorrow. It should be interesting. Please take a look at the credits segment. It will point to other resources for additional research. Thank you for watching.